Okay. Students, during last lecture, we discussed about the scheduling algorithms. We saw shortest remaining time first algorithm before this. Before this, we saw shortest remaining time first algorithm. Okay. Next algorithm is a round robin algorithm. This is also preemptive algorithm. This is also preemptive algorithm. SRTF, shortest remaining time first, is a preemptive algorithm. Like that, round robin algorithm is also preemptive algorithm. Okay. So here we assume 6 processes. Arrival time of each process has been given, and the burst time of those processes also given. Okay. Now, this is preemptive scheduling. Okay. Process 1 arrives at 0th millisecond. Process 1 arrived at 0th millisecond. So here we will start from 0. Okay, we will start from 0. 1 second. So in 0th millisecond, process arrived. Okay, but before going into round robin algorithm, the round robin algorithm is a best algorithm whichever we discussed till now. Okay, even the shortest remaining time first also will reduce the waiting time considerably, but this round robin algorithm will completely we can say eradicate the starvation. Okay, of only one process waiting for long time to use the CPU. That is called starvation, right? So that will be completely avoided using the round robin algorithm. Okay. So in round robin algorithm, none of the processes in the multiprocessing system, okay, none of the processes in the multiprocessing system will experience starvation. Will experience starvation. None of the process will experience starvation. Okay. But here in round robin algorithm, there is a time period called quantum time. Quantum, Quantum, quantum. Quantum time. That quantum time will be decided by the operating system. For example, 4 millisecond, 5 millisecond, 2 millisecond, 8 millisecond. Okay, so this quantum time will be milliseconds. Now in this example, we assume that 4 milliseconds is a quantum time period. We will see what is quantum time. Now process P1 comes in 0th millisecond and its CPU burst time is 5 milliseconds. Our quantum time is 4 milliseconds. So whenever a process entered inside the CPU, it will be continuously it can be continuously stay in CPU only in quantum time. Maximum 4 milliseconds only it can be there, continuously use the CPU. After completing 4 milliseconds, even if it has remaining time to execute the CPU, it will not be allowed, it will be evicted. Okay. So every slot, if you see, it will be 4 milliseconds only, but some of the processes will have less than quantum time burst time, CPU burst time, no? Okay, then it will not be executed 4 milliseconds. Now, for example, P3, its CPU burst time is only 3 milliseconds. Then why it is going to be used the complete 4 milliseconds quantum time? It will not be. Okay. All other cases, the processes which are having more than quantum time, it will be allowed to use the CPU only in the quantum time period. After that, it will be evicted. So here, as per this example, it is nothing but 4 millisecond. So any process enter inside the CPU, it can use the CPU continuously only 4 milliseconds or less than 4 milliseconds. Okay, maximum it can use 4 milliseconds only. Okay, why this is supplied? Because then only all the processes will get chance. Okay, no starvation will be there. None of the process will go to starvation. Okay. Okay. Now process P1 entered. Its execution time is 5 millisecond, but it can use quantum time is 4 millisecond. No. So it used the CPU 4 milliseconds. So 0 time it started. In 4 millisecond it completed. Not completed. It has to be evicted because it is a round robin. Only it can use the CPU continuously 4 millisecond maximum. So it is evicted. Process P1 will be evicted. Okay, now 4 milliseconds completed. Process P1 evicted. Now 4 milliseconds of the P1 is completed. How much remaining time? Remaining time I put here. Okay. So remaining 1 millisecond, it has to use the CPU. Okay. Process P2 in the next milliseconds, because process P1 when it is completing the 4 milliseconds, process P1 when it is completing 4 milliseconds, how many process will be there? Process P1, all these 4 milliseconds may, except P6, all the processes will be there. All the processes will be there. Okay. Now here no shortest job first and all. Here only FCFS will be applied to choose the process. So process P2 came next. Its CPU burst time is 6 milliseconds. So P2 entered in 4th millisecond. It completed its task in 8 milliseconds. But 2 more milliseconds remaining, it must be evicted. It got evicted. Evicted process will go to ready queue. Remember, in objective type question, I may ask. Okay. Okay, evicted process, evicted from CPU. The process which is evicted from the CPU will go to ready state. Okay. If any process not has any IO, not completed any IO operation to proceed the execution in CPU, that will only go to blocked state. Remember, this question is very important. When the process will go to blocked state, when the process will go to ready state, from which state the process will go to running state, all these are very important. Okay. Abhi idhar dekho. So P2 entered, only 4 millisecond allowed. So 8 millisecond mein 4 milliseconds execution it completed. Remaining 2 milliseconds because its CPU burst time is 6 milliseconds. Okay. Next P3. So P3, why I am choosing sequentially? Because here round robin along with FCFS. We are using round robin along with FCFS. Of course, round robin along with the shortest remaining time also we can use. No problem. Okay. But commonly with round robin, this will be used. FCFS will be used. Okay. FCFS will be used commonly with round robin. Okay. Round robin is what? Round robin will say only the process should continuously execute the CPU in a given quantum time only. That's it. Okay. It will not choose the process based on any algorithm like other algorithms. Okay. Only quantum time is very important in the round robin. Okay. The sequence of the process, how it should be selected will not be said in round robin. So always a round robin need another algorithm. Remember. Okay, here we considered this FCFS, first come, first served. Okay, so process 3 next. Process 3 entered. It started, its execution time is 3 milliseconds only, no? So 8th millisecond it started, 11th millisecond it completed. So 0, here I put 0. That means P3 went out of the ready queue. Now currently P3 is not in the ready queue because its CPU burst time is 3 millisecond, which is lesser than the quantum time. So in the one shot itself, yeah, it got executed. Okay, next process is P4. P4's CPU burst time is 1 millisecond. So P4 will enter next. So 11th millisecond it will start, in 12 milliseconds. 12th millisecond it will complete its execution. P4. Okay. Then P5. This is a cycle. Okay. Chance will be given to all the process. Then again in another cycle, the chance will be given to in the sequentially all the process. So it will be cycle. Okay. So in the first cycle, now P5 entered. P5 entered. P5 CPU burst time is what? 5 milliseconds. 5 milliseconds. So P5 enters 5 milliseconds, but 4 millisecond only it will get to execute the CPU. 12 millisecond to 16 millisecond. 1 millisecond remaining for P5. Okay. And then P6 enters. P6 burst time is 4 milliseconds. Okay, it starts in 16th millisecond. It will complete in 20 millisecond. It's CPU burst time and quantum time are equal. So it will also complete in one cycle. Okay. So now P6 also will be evicted from the ready queue. So now P6 will not be there in the ready queue. P6 will not be there in the ready queue. Okay. Okay. Next, one cycle got over, P1 to P6. Now again in the second cycle, P1 burst time 1. So P1 will be executed 20 to 21 millisecond. And then P2 is remaining 2 milliseconds. So P2 will start 21 millisecond. It will be executed from 21 to 23 milliseconds. And then after P2, P3, no remaining time. P4, no remaining time. Then P5 has only 1 millisecond. Then P5 enter, it will be completed in 24th millisecond. That's it, simple. Okay. But if you apply the shortest remaining time first algorithm, what will happen? We should consider the arrival time, and in that time, arrival time, and at that time, what are the processes are available? Okay, which process has smallest CPU burst time at that point of time, that will be selected. Among the available process, whichever process is having shortest CPU burst time, that will be selected. Okay, so you should know that that can also be applied. Okay, along with the round robin. Okay, now here for this you have to calculate the completion time, turnaround time, and waiting time, and average waiting time. Okay, this you can do as homework. Okay, and tomorrow you can show the output. We will discuss. You can confirm whether your answer is correct or not. Remember, you have to calculate the completion time, turnaround time, and waiting time, and then average waiting time for this. Okay, so please take the snap of this. Take the snap, then only you can calculate. Okay. Till now, we have seen only one service, one of the services, we can say, one of the services of the operating system. I said in the first lecture itself, the operating system will provide so many services. Okay. So, what are those services? For example, managing all the processes. Because in multi-processing system, managing all the processes are very important. Okay. So managing all the processes, that is called the process management. That's what we saw. Now, memory management. Memory management is another service, or we can say another task of the operating system. This is the second task which we are going to see, memory management. Okay. Memory management. Why for memory management the operating system is required? Why? Because we don't have enough space in the memory. Which memory? Main memory.
Ma'am, have you unshared
Yes.
your screen?
Sorry. You
Have
did
you
not see.
have you unshared your screen?
Oh, you couldn't see. So till now I explained without sharing or what?
No, ma'am, it was visible earlier. Now it is not visible. When you
Okay.
said to take screenshot, till then it was visible. So if you're talking with me, I'm.
Okay. So I hope now it will be visible.
Ma'am, who decides the quantum time?
Quantum time operating system. I said no, operating system will choose the quantum time, but there is a large, the efficiency of the round robin algorithm will be completely depend on the quantum time. Why? Because quantum time should be decided, deciding the quantum time is very crucial. Why? Because that is completely depending on the CPU burst time of available processes. Why? Can you think? See, suppose quantum time, I am keeping as 10 milliseconds. 10 milliseconds is a quantum time. Okay. But whatever processes are arriving, no, all those processes CPU burst time are within 5 milliseconds. Okay. फिर क्या हो गया? It will work exactly like our first come, first served. There will be no difference. Getting my point? Quantum time, if I keep, I am not, if operating system keeps quantum time is a long time, 10 milliseconds, and at the same time, whatever processes are arriving, all are having what? Very small CPU burst time. Okay. Please try to think. Okay. So 10 milliseconds is a quantum time, but the process is first process, for example, 2 milliseconds, second process 3 milliseconds, third process 1 millisecond. I mean, now how the execution will be? Exactly how in FCFS. It is nothing but FCFS algorithm only. First, which process came first, that will be executed. Okay. So deciding the end at the another side, you are keeping very small quantum time. But whatever processes are coming are having very large, lengthy quantum. What will happen? So many cycles, which will increase the waiting time. Okay. So deciding the quantum time should be now operating system will know that what are the applications are there, what is the applications execution time of each and every instruction. See, you studied about the microprocessor, so one cycle instruction, two cycle instructions and all, you know. Okay. So depending on all those factors, the operating system will decide the quantum time. So deciding the quantum time is challenging. Matlab, it is very crucial. It has to consider so many factors. ऐसे नहीं है 4 millisecond, 10 millisecond it will assume. It will see the average execution time of all the instructions, all the types of instruction. Types of instruction, why I'm saying, see, your computer may be different architectures of computer. No, your computer may be von Neumann architecture, another computer will be the Harvard architecture. Abhi instruction will, execution of the instruction time will vary. So all these factors will be considered by the operating system, and then the quantum time will be decided. Okay. Okay. So memory management. Memory management, why we need the memory management? Why we needed the process management? Why operating system should manage the process? Because multiple processes can be executed at the same time. Okay. Each process should not interfere with each other. So for that, inter-process mutual exclusion is necessary. Okay. When more number of processes are waiting in the ready queue, somebody should be there to schedule it. Okay. Now in your classroom, what happened? When you came to college, what happened? Nobody was there to control. Everybody just grouped together to sign the attendance register. What will happen? It will damage the attendance register. There is no systematic, nobody is there to manage that process, that task. So everyone will, because everyone want to complete your work immediately. So everyone wants to sign immediately. Okay. So there should be a systematic way. First row students, and then second row, and then third row, or otherwise next day. First last row, and then last before row. Some systematic way should be there. No. Then only smoothly it will go, and the attendance register will not be damaged. No. Attendance register will not be damaged. Otherwise, all will just pull here and another one will pull there. Then it will damage the attendance register. And it is not the systematic way of working also. Okay. So like that only here also, multi-processing system may multiple processes. Each and every process, their requirement only very important. So someone should be there to say you should go first, but simply not. Now I am saying attendance register. Now everybody has to sign. First, for example, I am saying Aishwarya should sign. Next, Sweetie should sign. Both are sitting in one is sitting in one corner, another girl is sitting in another corner in the classroom. Ye kya hai? Now this is not the systematic way. It will increase the time unnecessarily. So either I have to say that first row first and then second row, or last row and then last before, coming from back to front, or front to back. Something should be there. Okay. Like that only, when multiple processes are there, by following something, some algorithm, the operating system should decide which process should use the CPU. It is not like randomly it will pick up any process and you can execute the CPU. Then it is not following any it is not considering other factors, because allocating the CPU for the processes will considerably enhance the working of the processor. Okay. The processor speed is also depending on the scheduling time. Okay. So that you have to remember. So it will increase the speed of the processor. Of course, increasing the speed of the processor is the only motto now. Okay. Chalo, we will start. Okay. So memory management basics. Why we need memory management? Because our RAM, which is required by many number of processes, it is very less in capacity. Okay. You may ask, ma'am, why are you saying always RAM is small? Why can't you increase the size of the RAM? Okay. If we increase the size of the RAM, now you are buying the laptop in abhi costly, but what on 35,000-40,000 if you spend, you can buy. In the same situation, I'm saying that 2 lakhs you have to spend to buy the laptop, because we increase the RAM. RAM is very costly. So it is affordable?
No.
It's not affordable. Okay. So we can't increase the, somehow we have to manage keeping the RAM small. Okay. So RAM is what? RAM is during the execution, RAM is required by all the processes. If in multi-processing system, there are more number of process comes, all the process wants to use the RAM because multi-processing system means what? All the multiple processes will be executed simultaneously. So all need space during the execution to store the temporary data. Okay, so RAM is small. That is the main reason we need a separate manager. Who's what? Who's operating system. Okay. Another one, the memory is different hierarchy. There are some memory we are calling which is very small but is very fast. Some memory is medium fast, okay, but very costly. But this is medium fast comparing with cache. Okay, main memory is medium in speed. Capacity is little more than cache, And disk, we have so much storage capacity, but it is very slow. So these are different what hierarchy of memory. So then you may ask, ma'am, different hierarchy, this different hierarchies are there. Then what here in hierarchy, what the operating system will do? See, when very small RAM is there, okay, we have small RAM, okay, there are more processes, okay. Somehow we have to give space in the RAM, okay. But the rest of the, for example, assume that there are 10 processes. 10 processes are currently there in the multi-processing system. 10 processes will share the RAM, okay. 10 process it is not like that. Always remember, see, it is not like that. One process will use in a multi-processing system. When 10 processes are there, only 5 process will use RAM, another process will use disk SNA. Remember, okay. All the 10 processes we have to give RAM to some memory, even if it is small. Rest of the part of the processes will be stored in the disk, but that will not be stored in the disk as a secondary memory, as a virtual memory. We will discuss about the virtual memory little later, okay. So there are different hierarchy of memory. When 10 processes are there, half part of the process will be in RAM, just approximately I'm saying. Half part address space, okay, address space, half address space of the all the processes will be in RAM. Remaining of address space will be there in the disk, but it is little quickly accessible. There is a portion of the disk which will be allocated as a virtual memory, okay. So when one process, one half of the process is there in a RAM, remaining half during the execution, it is needed what we have to do, what the operating system will do. It has to see the address of the RAM where the process is stored, and then it will go and see the address of the disk where the remaining part of the process is stored, okay. So address, now address of the RAM is not equal to address of disk. That is obvious because disk is what? Very big and RAM is very small. RAM has very small capacity. Then how the addresses will be equal number of addresses. RAM will have less number of addresses to denote each and every memory cell. Disk will have more number of addresses to denote each and every memory cell. So suppose here memory cell 1000 may I am storing process 1. Same memory cell 1000 may I can't store the another part of the same process in disk, virtual memory. That is another issue because here address translation should be done by the operating system. It will take some process, it will searching some part of the process here. It is not available in RAM. It will go to disk, and where in the disk it will search disk to itna bada, then where exactly it has to know in which address what I am searching for that data is. It should know already, okay. So then only quickly it can retrieve. Okay. So that is another issue. Okay. So memory manager has the job of using this hierarchy to create. Memory manager is what? Part of the, how scheduler is part of the operating system. Like that, memory manager is a program segment in the operating system. It will only handle memory management related tasks. Okay. So memory management has the job of using this hierarchy. But to the processors, what it will show, this is what in the first lecture itself we saw. For all the processors, no, all the programs, applications, the operating system is an abstraction. Okay. Actually, what the operating system is doing, no, that will be hidden for the application processes. Okay. So that abstraction, now now you are studying that cache memory, main memory, disk is there, then only you come to know, no, all these different types of memory are there. But when you casually using the laptop and all, you will not think about there are different memories there, so address should be translated by the operating system. So for to do that, there is a memory manager, that and all you will not know. Yeah, everything is hidden. All the complexity will be hidden by the operating system. So that is called the abstraction. That means it will create some illusion, like which is not original. Originally, it is doing so many work, but for the processor now, what the processes, that means applications, they will think that okay, we have RAM, so whatever we are storing, it is getting stored in a RAM. Okay, it will give a feel, illusion like that to the application processes. That means it is simply, you may ask why it has to create a abstraction, because application programs no need to know anything about the system, because once if it knows, no, it will create a program to crash the resources. So it is not necessary, unnecessarily it has to be visible to the users. Okay. So it is creating abstraction. Memory abstraction will be created by the operating system to the processes. Here applications are nothing but processes. Okay. This is why we need what? We need the memory management. Okay. So we need operating system to manage the memory. Okay. Okay. Three simple ways of arranging memory with OS and one process. If only one process is there, there is no, matlab, operating system is not needed only actually. Okay. When only one process at a time, it will be executed. Okay. But here it is given three simple ways, but there are many ways are there to arrange the operating system and single process in a uniprocessing system. Okay. Just simply they have shown the three which are commonly used, usually how it will be located. The user programs and operating system will be located in three ways, common three ways. One is user program will be there in a RAM during the execution, and operating system will also be there in a RAM during execution. Okay. And then the second way, operating system will be kept inside the ROM, user program will be there inside the RAM. Okay. And then operating system will be there in RAM. Here actually it takes some time, no, to boot. Okay. So here operating system is there in RAM, user program is also there in RAM, but device drivers as a part of the operating system, that will be separated and put inside the ROM. Okay, these are three different ways we can, not we, there were the memory and operating systems arranged. Okay. This is not important. Okay. Important is this. Memory management strategies. There are three different memory management strategies. No memory abstraction. Always remember, no memory abstraction, matlab what? No abstraction. That means operating system did not create any illusion at all in this. Okay. It is not necessary the operating system should create illusion. That means abstraction, because one process at a time. Always when you look at the memory, no, memory. You're talking about the memory management. When you look at the main memory, students, here we are talking about only main memory. Okay, only main memory. The operating system has another task, another service, which is called disk management. Okay, there we will study about how the disks are managed by the operating system. Here we are seeing about only how main memory will be managed by the operating system. Okay, there are so many services the operating system will provide. One is process management, then memory management, disk management. Disk management is also called as file management, file management, etc. Okay. So here we are seeing about only main memory. Okay. So no memory abstraction. That means at any point of time, if you look at the main memory, only one process will be there. Okay. So when one process is there, it is very simple. No, it is very simple, but it is very big limitation. The processor speed will be very slow. If only sequential execution will happen. But when one process is there, there is no need to manage the memory. The full entire main memory is for only one process. Okay. So it is not necessary half part of the process should be stored in the virtual memory, and whenever it is needed, it should be retrieved. All those complexities are not there here. Okay, so that is no memory abstraction. Okay, and we have another strategy which is called swapping and compaction. Compaction is actually not the memory management technique. Swapping there is a drawback. Okay, to overcome the drawback, we apply compaction. Okay, so swapping is a second technique. In swapping, what will happen? The entire program. That means in that case, it is not in swapping. It is not a single process will be there in the main memory. Single process will not be there in the main memory. There could be more than one number of processes in the main memory. More than one number of processes can be in the main memory. But it is like the entire program. If suppose one process should be executed, the entire program of that process will come to the main memory. Okay, it is not that time no facility was there to this was not invented to keep a half of the process in one memory, remaining half whichever is going to be executed immediately will be there in a RAM. That was not there. Okay, that time the operating system used swapping as a technique. And then this virtual memory concept came. Okay, so in virtual memory, after the virtual memory concept came, then we can use more number of processes at a time, and we allocated a part of memory, disk memory, as a main memory, and then address translation. Through the address translation, we retrieved the data. Actually, after virtual memory invented, only the address space concept came. Address space. Okay. You just think now why the address space was not there in the previous two cases. You know what is address space? Address space is a separate accessible memory space for each and every process. Okay. Now, when no memory abstraction is there, of course, only one process. So there is no need of address space. Only one process. No, so entire memory is going to be used by the RAM, used by the single process. Entire RAM will be used by the single process. So that is why we have to split the memory into different address spaces. It is not required. Okay. During swapping, also address space is not required. Why? Entire program we are keeping in the main memory. So then only very few programs, even those programs are small, only few, one or two programs, two or three programs we can keep at a time in a main memory. Okay. If the if main memory filled, I am talking about swapping. If suppose there are three processes, but all the three processes, entire program currently is there in the main memory. So main memory filled. fourth process is coming. Okay. So one fourth process coming for the execution, any one of the processes which is already there in the main memory should be removed and kept inside the disk. Entire program. It will come inside the main memory, go out of the memory entirely only. That means only entire program will go out and entire program will come in. It's not a part of the program. Okay. So very few programs we can keep in the main memory. Swapping, that's called swapping. When new process comes, there is no space in the main memory, then there is a swapping. What is the process here in the main memory? That will go to the secondary memory, and which process has to be completed, its complete program will come to main memory. Okay, this is called swapping. Okay. So through the swapping, the operating system managed the multiprocessing. But then address space comes, what we did, we kept the complete program in disk. Whichever part of the program is required, only that part will come to the respective address space. Okay. So, but here also, if suppose the system filled, swapping, not swapping, it is called context switching. Okay. That we will discuss. Context switching will be there here also. But here, program going outside and coming inside, both will be as the entire whole program only. Here it is not like that. The whole program will be there in disk only. In that, whichever part is going to be executed of that particular program, that will come to that related to that instruction will come to the address space, and that those instruction will be executed. Okay. Okay. Students, there is a 15 minutes break because you beyond this you will not listen if I did not give break. Okay. You need break. I think you need break, right? Yes or no?
Yes, ma'am, we need break.
Yes, ma'am.
Right. So 15 minutes break you take. And
But
And but when the lecture
yeah,
will end?
5:46.
yes,
Oh
ma'am.
my
I
God.
also think this.
Yeah, it is like I am taking so much time, but I couldn't complete. I thought I decided whatever I have to complete now. Abhi wo bhi nahi hai, Rama. Chalo, then you wait just 5 minutes, 5 to 10 minutes. Let me complete and then I will send you. Okay. Virtual memory abhi ho gaya. Next. This is swapping. Okay. This is swapping. But before that, I have to say about the this also, no, something no memory abstraction. Matlab only one process at a time. Okay. Till 1980, all the computers used this only. No memory abstraction. Okay. That means only one process can be executed at a time. Okay. Till 1980. It could be anything. For example, mainframe computers. Before 1960, we used mainframe computers, and before 1970, we used mini computers, and before 1980, we initially the initial period of usage of the personal computers. All those period, mainframes, mini computers, personal computers, till 1980. Personal computers still we are using. So personal computers till 1980, whatever we used, everything, all the computers have this only, no memory abstraction. No memory abstraction. Okay. So here what is actually only one process at the time can be running. Only one process can run. As soon as the user typed another command, when typing command or clicking and enabling something, the operating system will copy the requested program from the disk to memory and it will execute that. Okay. Getting it? See. Now only one process. That process is executed. Okay. Then the next, whenever the next command comes, the memory will be free only. Okay. Because the process already executed process also completed. No. When new process comes, you have to create, right? You have to type something to create the process. For example, in a you are seeing the DOS operating system. How are you creating process? By typing only you're creating process, no? So by typing you can create process, or by clicking something, or also you can create process. Whatever, however you're creating a process, that new process is created, the operating system will copy the requested, because the entire program should be copied, no, requested program from disk to main memory. But that time also only one process will be there in the main memory. Please understand. Okay. So then that process will be executed. In between any process, even if you enable also, the current ongoing process should be complete. Okay. Then that process completed, new process comes. What the operating system will do? The operating system overwrite the new program into the already existing program in main memory. Okay. Why it is overwriting? Because a previous process execution got over. Now new process comes. New process ka entry, complete program should go to main memory. Okay. So main memory, already the program will be there. Previous program ka complete code will be there. On that, this code, new code will be overwritten. Overwritten means the overwriting will, obviously it will delete the previous entry, no? Okay. So only new entry will be visible. Okay, so that is no memory abstraction. No memory abstraction, only this much you write. This content, no, this content what I said, which is there in page number 174 in Tenenbaum. Printed page number, not PDF page number. Book mein print hua na, that page number 174. Page number 174 mein this is there. Okay, so you can study using that. Okay, then swapping, note down 174. You don't ask later. Okay, so next is swapping. Now we will see how the swapping will happen. What is swapping? You have to know this. Running multiple programs without any memory abstraction is called swapping. That means no, it will not show that the it will not create any illusion. Okay. No memory abstraction. See, simply no memory abstraction, wherever the address space is not there. Once the address space came, only the abstraction came. Why? Because when address space came only, when address space concept invented only, we started to use the virtual memory and main memory as address space. No, both the memories. So we should hide this. We are using the virtual memory to store the address space. Okay. So whenever the virtual memory started to use, there only there only the memory abstraction will be there. Okay. Before that, no memory abstraction. No memory abstraction because it was not needed. No memory abstraction because it was not needed. Okay. Now look at this diagram. Okay. There's this line, the stripes, these are empty space. Okay. Assume that there is an operating system in RAM during the execution. Okay. Process A comes. This is about swapping. Assume process A comes. Of course, by the time all entire RAM is free only, so process A's program will occupy the. You should not forget the entire program, that word here in swapping. Okay. So the entire program will come to the main memory. Okay. Now program A, this process will be executed. Now assume that process B comes. Again, we have space in the main memory because process is less, small process. Than this process ka memory, the process needed memory lesser than the free space of the main memory. So it also got occupied. Then process C comes, that also occupied the main memory. Okay. Now here process A, B, C are there, no? process A is evicted, we can say. Okay, process A, we have to see process A again it is coming, no, so it is not completed its execution. So it is going maybe because of any IO request or something like that. So the process A will go to disk. Okay. Then which process? Process D comes. Process D clear this space is not sufficient. Okay. So the process D take this free space. Okay. Now process D also occupied the main memory. Okay. Now where currently process A is there in the secondary memory. Why it went? Maybe the new process arrives. Okay, so that the swapping might have happened. So it got swapped out to disk and D is swapped in to main memory. Okay, swapped in main memory. Okay, swapped in main memory. Okay. Now next process B, because next process A wants to use the CPU. So process A should come. So for that, which process should go? Process B should be swapped. Okay. So process B swapped out to disk. Process A swapped in main memory. From where? Process A from where it came? It came from the disk. Okay. So like this, using swapping here and there. What here and there? From main memory to secondary memory to main memory, but entire program. That is very important. If you forget that word, no mark. Okay. Entire program will be swapped in, swapped out. Entire program will be swapped in, swapped out. Okay. Like this, the multiprocessing happens. This is just little advantages than the single processor execution, uniprocessor system. Okay. Now here, what you will write about the swapping. There are two memory management strategy which will allow multiple processes. Two memory. See, totally there are three strategies, but we are not considering no abstraction because that is a uniprocessing. No. So there are two processes, two strategy. These are memory management strategies. What? Swapping and virtual memory. So the swapping and virtual memory there are multiple processes can be executed. Okay. But when comparing with virtual memory, swapping very less number of processes can only come into the multiprocessing system. Okay. So how the execution will happen here? That about the first two strategies you will write, and then this is very simplest multiprocessing strategy. This is called swapping. Okay. The entirety of the program will come inside the main memory and go out of the main memory to disk. That is second point you have to mention. And then like this, any diagram you can draw, and then you can show process A came, B came, C came, now filled. Memory filled almost. Next process which is coming, no, that requires more space than this. So cannot be scheduled. In that case, what should be done? Any one of this process should be removed, right? Okay. So process A removed. Why? Because process A, maybe the algorithm, process A came first, no, to memory. So process A is swapped out. Okay. When it is swapped out, where it will go? It will go in a disk because later it should come again. Okay. Now free space, process D came. Okay. Now again, process D came. Again, process A wants to come. Process A should be executed. Process A actually should be executed, but because to give the space to process D, it is swapped out, right? So then we removed the process B. We swapped out the process B to the disk, and process A came. and occupy the space. So this is just an example for swapping. So this diagram for swapping you have to draw. What is the difficulty here? What is the limitation here? What is the limitation? The limitation is if you look at any point, there will be so many internal fragmentation. Why internal fragmentation? Matlab what? Here and there, scatteredly, there are many space. We देखो here, sort of space here, little space. Now, what will happen because of the internal? Why it is internal fragmentation? Because inside the main memory, it is happening. So it is internal fragmentation. It is internal fragmentation. Okay. So, what is the disadvantage here? So many free spaces would be there here and there. Here and there. Assume that here this is 8 bytes. Oh no, this is 10 bytes. This is 20 bytes. Okay. 10 bytes, 20 bytes. Okay. 25 bytes, new process comes. 25 bytes, new process comes. There is a space, of course, because 20 plus 10, 30 bytes are there, but still you can't allocate. Why? Because the free spaces are scatteredly there in the main memory. You can't allocate. Though you have free space, you can't allocate the new process. Okay. So for that, what we can do, we can put all the processes, we can pull all the processes down, all the cells, and we can put all the free spaces on the top, or either way. Okay. That means all the processes which are stored should go contiguously in one location, and all the free spaces should be contiguous in the main memory, not continuous, contiguous in the main memory. Then we can, that process, keeping all the free spaces together, that is called compaction. Keeping all the free spaces together is called compaction. But compaction is not at all a suggested solution for this, because when you will do compaction, you tell me how the operating system will decide when we have to do the compaction. Whenever more number of free spaces scatteredly found here and there, and there are many processes are waiting to come, then only it has to do the compaction. But doing the compaction is not a simple process. Now this is a small diagram, so only 2 free spaces are shown, but actually it will not be like that. Okay, there are so many scattered fragmentations. So all the fragmentation you have to, all the fragments you have to keep it together. Okay. So that will take very considerable amount of time. Okay. So when it is doing compaction, no execution can happen, right? Because it is rearranging the processes here and there. So that time how the execution can happen, how the data in the memory can be used, not possible. Okay. So that will take more time. Compaction will take more time. So that will degrade the speed or performance of the processor. So it is not the suggested one. Okay, so this has a strong disadvantage of this. Holes, here they mention holes, holes means free space. This free space are generally called holes. Can compact holes by copying programs into holes. This takes too much time. So this is the disadvantage of compaction. Okay. So I will finish the memory, sorry. I will finish the lecture here, otherwise you will kill me. Hello. Thank you, students. Thank you so much.
Yes,
Thank
thank
you,
you.
Bye. 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 Take care. So tomorrow, your tomorrow schedule, I will just message now. Okay, after confirming with the Archana ma'am. Thank you, students. You all can.
Okay, ma'am.